Now we are going to start with the conductivity of the solutions. So what we see about the conductivity, that we have actually two types of conductivity of the solutions. Right, one is the molar conductivity. One is the molar conductivity and other is the equivalent conductivity. Other is the equivalent conductivity. Right. So what happens in this case, like when we talk about molar conductivity, like first of all you should know that both the conductivities are particularly the conductivity for the solution, not for any specific part. We are talking of the complete solution here. So what happened when we talk about molar conductivity, it is represented by lambda m. So lambda m here is equal to kappa upon concentration. That means it is equal to conductance or conductivity, specific conductivity divided by concentration. Right. And when we talk about equivalent conductivity, it is denoted by lambda E and it is equal to kappa upon concentration. Here again kappa is the specific conductivity and C is the concentration. So as you must be thinking that both the terms appear to be same, like as I wrote the formula, but actually they are not same. The difference here is that in this case the concentration is expressed in molarity and here the concentration is expressed in normality. So that means this equation becomes lambda m equal to kappa upon molarity. And suppose if we take volume in centimeter unit, if we change the unit of the volume from liter to that, so it becomes, you may write the equation as this thing, kappa into 1000 upon molarity. And in the same way here we can write that lambda E is equal to kappa upon normality. Again we are changing the units of volume here, so you can also write kappa upon normality, kappa into 1000 upon normality. And if we talk about the whole thing, that is the units here. So units of kappa we know is Siemen and it is going to be centimeter square per mole. Similarly here it is going to be the Siemens centimeter square per equivalent per gram equivalent. So this is going to be the unit. Now if we talk about that, what is actually, like if we take conductivity, suppose we take molar conductivity and I take one more thing, that is the kappa, that is the specific conductivity. Now we will see that what is the difference that exists between the molar conductivity and the specific conductivity. So the first difference is that molar conductivity is denoted by lambda m and it is denoted by kappa, right. The second difference is that it actually gives us the conductivity for the whole solution. It gives us the conductivity of the whole solution, but it gives us the conductivity for a specified part, or you can say it gives conductivity for a small region or a specified part. Therefore it is called as unit factor. Therefore it is also called as unit factor. Now if you dilute the solution, like I'll write the point here, then I'll explain you that what happens here, molar conductivity increase with dilution, we'll write with dilution. And then in this case what happened, conductivity decrease with dilution. Now the first thing is that what is dilution? Dilution means we are adding what? We are just increasing the amount of solvent in a solution. That means we are adding, like if a solvent is water, so I'll say that I am adding more water into it and I am making the solution less concentrated, right. So what happened here, we say that molar conductivity increase with dilution and here molar conductivity decrease with dilution. Now let's see that how they both vary in a different manner. Suppose you have a beaker in which I have a solution. Let's say my solution is still here. for a given concentration, right? Now what I'm going to do is, I'm going to dilute it, and when I dilute it, you can say that now this area, this given quantity changes to this much. So this is my, let's say the initial one was A, the level was A, now on dilution it becomes B. So what do you think that about the molar conductivity? So as we have diluted the solution, that means the number of ions will be more now, and we know that molar conductivity depends upon the number of ions. So as the number of ions are increasing, so that means the conductivity is increasing. So that is why I wrote that molar conductivity increase with increase in temperature with dilution, because on diluting the number of ions are increasing, and due to increase in the ions the conductivity is increasing. But if we compare with specific conductivity, so we say that, like, if I want to calculate specific conductivity of this part, so I'll say that this, like, for this given region, the conductivity is called as kappa. The conductivity is called as specific conductivity, that is kappa. So now when I will dilute it, so that means more number of ions from here, let's say positive or negative, what kind, other different kind of ions, they will actually diffuse out now. They will actually diffuse out, because when we will dilute, the ions will be more random now. So there will be less number of ions inside this portion, and as it will have less number of ions, so that means the conductivity will decrease. So this is how we can say that conductivity increase with dilution and conductivity decrease with dilution. I think you got it. It is for a whole solution, because when you are diluting it, you can say volume is just increasing. So therefore there are more number of ions now, and we know that conductivity is directly proportional to the number of ions. So more ions, that means more conductivity. But if we talk about kappa is for a small area, right, a small region. So when we dilute it, the number of ions present in a specific region will be less, because they will just ooze out from that area, and due to that we will say that number of ions in that given area gets reduced, therefore the conductivity decrease with dilution. So this is how you are going to explain the molar conductivity and the specific conductivity. I think it's clear with you. Now we will take in another topic. As you all know that we have electrolytes. You all know that we have electrolytes. And you know that electrolytes are the substance which dissociate into ions when current is passed. We all know that. We know that electrolytes can be strong, electrolytes can be weak. That means strong electrolytes are those which completely dissociates to give all its ion. And weak electrolyte is that which partially dissociates to produce ions. So that means if we talk about the strong electrolytes, all the ions are being dissociated. That means there is no such undissociated molecule left in the solution, because that molecule is completely dissociated to form ions. So we will find only ionic form in the solution. But if we talk about the weak ones, they are partially ionized. So you will be getting the ions, along with that the unionized molecule. I think you got it. We will get the unionized molecule, and as well as with the ions, few ions we will get. So if we talk about alpha, so for strong electrolyte, alpha is equal to 1. Alpha is equal to 1. But for weak electrolyte, it is less than 1. It is less than 1. So this behavior, like the conductivity, like now if we talk about the conductivity, because we know that here the factor which is responsible for the conductivity are the ions, and as I told you that in strong electrolyte ions are more, and here in weak the ions are less, because there are unionized molecule also present. So likewise they will differ in the conductivity as well. So there is an equation which actually tries to express that how the conductivity get affected or changed for a strong electrolyte and for a weak electrolyte. So we have a mathematical equation for that. What's that? Let's see. It is, I'll just divide it so that you should not get confused. So what happened, there is an equation called as Dubé-Huckel equation. Dubé-Huckel equation. This equation says that lambda m is equal to lambda naught m minus AC raised to power half. This is the equation. Now you know that what is the meaning for this equation. This, let's see that what symbols actually signify first. This is the molar conductivity for any substance. This is the molar conductivity for any substance. And this is the molar conductivity, or you can say a limiting molar conductivity at zero concentration, or we can say at infinite dilution. So this is molar conductivity at zero concentration or at infinite dilution. And this A here is a constant, and the C here is a concentration, and the C is a concentration. So now what happened, like again I'll just signify the symbol again. This is the molar conductivity for any substance, maybe for a strong electrolyte, maybe for a weak electrolyte, any substance. This is the lambda naught m, which is the molar conductivity at zero concentration, or we can say at infinite dilution. This is A constant and this is C is the concentration, right? So this expression we have. So now you know that what is the value for this A. The value for the A is same for same type of electrolytic solutions. Now, what kind of electrolytic solutions I am talking about? I am not talking about the strong and weak electrolytic solution. I am talking about a different kind of solution. We have 1:1 kind of electrolytic solution. We have 2:1 kind of electrolytic solution. We have different kind. For example, let's see. Suppose I have NaCl. So in this case, what we see that Na has positive valency and even Cl has -1 valency. So both valencies are same. So we can say that it is 1:1 kind of electrolytic solution. Similarly here, if I'll take an example, let's say I'll just take an example first, then we'll take that what kind of it is. Like I have MgCl2. So here the valency is +2 and here it is -1. So that means it is a kind of 2:1 kind of solution, right? Likewise, if I take another example, let's say we take aluminium chloride. It is 1, we know that it is 3 and this is negative. So it is 3:1 kind of electrolytic solutions. So we say that the value for a constant A is same for same ratio of electrolytic solutions. Like all the solutions which have the value that are 1:1 electrolytic solution, the value for A will remain same. All the solutions which have the same value, that is which are the 2:1 electrolytic solutions, the value for A will be same for them. So similarly, for different you can say X is to Y type of electrolytic solution, the value of A is going to remain same irrespective of the ions. So this is what it will help us in calculating the molar conductivity for a strong electrolyte and for a weak electrolyte. Now let us plot a graph in order to explain it. So let's draw a graph first. Suppose I am going to draw a graph for a strong electrolyte first. So I am just going to see that how the conductivity gets affected with change in the concentration. So suppose I have a graph and I am doing it for a strong electrolyte, and the conductivity for a strong electrolyte you can say is more, therefore we can easily calculate it, we can easily explain it, or we can easily plot it. So suppose this is my molar conductivity for any strong electrolyte and this is the concentration. So I am going to plot a graph between them. So we see that the graph appear to be, suppose I say like this. So that means I am just decreasing the concentration. As you can see, we started from here. As we are decreasing the concentration, we see that like as the concentration is like suppose you can have this kind of thing. Like for a strong electrolyte, again I am explaining. Suppose for a strong electrolyte, we are plotting molar conductivity with the concentration, right? So we see that that when we are diluting, the molar conductivity is somehow affecting. So if I just extra plot it, so this value of this point is going to give me molar conductivity at zero concentration. As you can see, concentration is decreasing here. So this is going to give me the molar conductivity at zero concentration, or we can say at infinite dilution. So we see that the graph for a strong electrolyte appears like this in this case. And if we plot a graph for a weak electrolyte, So the first thing is that it is very difficult to plot, difficult to measure even. So what kind of graph we get? We get a graph like this. So as you can see that if we keep on increasing this line is never going to meet this thing. So that means, because we know that the point at which this line meets this axis indicates the molar conductivity at zero concentration or infinite dilution. But in this case we don't have such value, because as we go on increasing them or elaborating them, they are never going to meet up, right? So that means this is going to be lambda m, and here the molar conductivity will be very, very less. So that means on dilution, the conductivity for this thing, molar conductivity for this thing, weak electrolyte, is again difficult to calculate. So this is how you're going to explain the Huckel-Onsager equation, just to show a molar conductivity, right? So we'll take up our next topic now, that is the law. So just look at the point.